All right, today we are diving into one of the coolest and honestly most revolutionary pieces of tech in space travel, the ion thruster. We're not talking about brute force here. We're talking about a super persistent, really gentle push that can take us to the farthest corners of our solar system.
So just imagine for a second, you're trying to plan a trip, not across the country, but across the entire solar system. Right away, you've got a massive problem to solve.
And that's the real challenge, isn't it? Your typical chemical rockets, they burn through all their fuel in just a few minutes. For a mission that's going to take years, you'd literally need a fuel tank bigger than the spacecraft itself. It just doesn't work. So, how do we get around that?
Well, this brings us right to what engineers call the deep space dilemma. It's this classic trade-off you have to make between raw power and sheer endurance.
Think about it like this. A chemical rocket is a drag racer. It's got this insane, powerful thrust that you absolutely need to break free from Earth's gravity. But it burns out incredibly fast. An ion thruster, on the other hand, is a marathon runner. Its thrust is unbelievably low. We're talking about the same force as the weight of a piece of paper in your hand. But, and this is the key, its fuel efficiency is completely off the charts. It can keep accelerating, just a tiny bit, for months or even years at a time.
So instead of relying on a massive, super short-lived explosion, we had to get creative. We turned to a much more elegant solution, a totally different kind of push, all powered by electricity.
And this right here is the big aha moment. You would never, ever use an ion thruster to launch a rocket from the ground. Its tiny little push wouldn't stand a chance against Earth's gravity. But once you're already out there, in the vacuum of space, that constant, unbelievably efficient push is exactly what you need for the long, long journey.
Okay, so let's pop the hood and see how this amazing piece of technology actually works. I mean, how do you turn a bit of electricity and some inert gas into a way to travel the solar system?
You know, at its core, the concept is surprisingly simple. You start with a propellant, usually a gas like xenon. Then, you use electric power to zap the xenon atoms, which strips away some of their electrons. This turns them into positively charged ions. And then, a powerful electric field acts kind of like a slingshot, launching those ions out the back at incredible speeds, and that's what creates your thrust.
And just a quick refresher on the absolute star of our show, an ion. It's really simple. All we're doing is taking a normal, neutral atom of xenon gas and just knocking one of its electrons off. That leaves the atom with a positive charge, which is absolutely crucial because now we can grab onto it and control it with electric fields.
So it all happens in this neat three-step process. First, you ionize the gas. You create those positive ions. Second, you use these electrically charged grids to create a field that grabs those ions and just flings them out the back. And third, and this step is so important, a little emitter shoots electrons into the exhaust beam. Why? Well, without it, the spacecraft would build up a negative charge, and it would start acting like a magnet, pulling the positive ions it just shot out right back towards it. That would completely cancel out all your thrust.
Now, this diagram shows a really clever trick for how that ionization actually happens. See, an emitter shoots electrons into the chamber, but instead of just flying straight, a magnetic field makes them spiral, almost like a pitcher throwing a curveball. This super long spiraling path makes it way more likely they'll smack into a xenon atom and knock an electron loose. It's like a game of subatomic billiards, and it's all designed to get as many collisions as possible.
And the result of all that acceleration? Those ions get shot out the back at speeds up to 130,000 miles per hour. Just think about that. This incredible exhaust velocity is the secret sauce to the engine's amazing fuel efficiency. In engineering, they call this high specific impulse, which is basically just a fancy term for gas mileage. It's how much oomph you get for every bit of fuel you use. And for ion engines, that number is just huge.
So look, this isn't just a concept on a blackboard or some wild idea. Let's look at how this technology has become real, proven hardware that is already out there exploring our solar system as we speak.
Yeah, ion propulsion is definitely not science fiction anymore. NASA's Deep Space One was the very first mission to use it to travel between planets. Then there was the Dawn spacecraft, which famously used its ion engines to orbit not one, but two different destinations in the asteroid belt, Vesta and Ceres. That had never been done before. Japan's Hayabusa mission used them to go to an asteroid, land, and bring a sample back home. And even closer to us, companies like Boeing use them all the time for station keeping on commercial communication satellites.
And here it is. This is what one looks like in the real world, a real flight-proven engine. This is a ZIS thruster, used on a ton of those Boeing satellites. You can see all the parts we just talked about. The chamber where the gas goes in, the magnets, those charged grids that do the accelerating, and the neutralizer. It's just a beautiful piece of engineering that takes all that theory and makes it real.
So, what does this all mean? What's the bottom line for the future of how we explore space? Well, to put it simply, this technology has completely changed what's even possible.
And it all comes back to this wonderful paradox, doesn't it? An engine with a push so gentle it couldn't lift a piece of paper off your desk is the very same engine that makes these incredible missions to distant asteroids and dwarf planets a reality. It's all about trading that brute force for incredible long-term efficiency.
This technology has already redrawn the map of our solar system. So the final question you have to ask is, as we build even more powerful and more efficient versions of these thrusters, where is this gentle, persistent push going to take us next? The moons of Jupiter? Saturn? Who knows? The possibilities are truly as vast as space itself.